Hi guys, so in this lecture video, I'll be discussing the Bohr model of the atom, which is an important model that provided us with the knowledge necessary for the later establishment of the quantum mechanical model. And so in this video, let's now go over the Bohr model. So using a blend of classical and quantum physics, Bohr postulated the model of the atom, and in this case he was studying the hydrogen atom, and he proposed the structure for the hydrogen atom as follows. So first, we have the nucleus in the middle, and surround the nucleus will then be the different orbits, and electrons are actually found in the orbits. So let's go over some of the important statements that Bohr concluded. So first, electrons move in circular orbit about the nucleus, and the motion of this electron right here can be described by classical physics, which involves wave equations. And here what it is. Now if we were to be taking this three-dimensional atom right here and cut it in the middle and smash this into a two-dimensional view, then this is what we're seeing right here. So these are the different orbits. And we're going to label this orbit as follows. Here it will be orbit n equal to 1, or simply just orbit 1, and orbit 2, and orbit 3, and orbit 4. So those are the different orbits. And inside this orbit, that we'll be able to find the electron. So electron, the second statement, electron has only a discrete set of allowed orbit, or is said to be quantized. What this means is that electron can only be found in this orbit right here, but never in between the orbits. So that's what this statement right here is saying, and that's what the term quantized means. So the term quantized, or the value they quantize, or amount they quantize, is then said to be limited to only specific value, and may never be between those values. And an example would be the step ladder, would be something that we would call quantized. So the step on the ladder, if you can imagine climbing on the ladder, then you have to step on the step, but never in between the step. So therefore, the steps on the ladder is an example of something that is said to be quantized. And here in this case, the electrons can only be found in the orbit. That's where they will locate, but never between the orbits. And the third statement is as follows. Electron can pass from one allowed orbit to another allowed orbit, so they can move around. And in such transition, fixed discrete quantity of energy that we call quanta are evolved, and that is either being absorbed or emitted. So now let's dissect this statement down a little bit. What this saying as follows. Electron can jump from one orbit to another orbit. So for example, electron can jump from orbit 4 down into orbit 3, or it can jump from orbit 3 into orbit 4, vice versa in the opposite direction. It can also jump from orbit 2 to orbit 4, or orbit 1 to orbit 2. So electron can be moving around or transition from one orbit to another orbit. But energy are involved in the movement. And what this is saying as follows. When an electron jumps from a higher orbit down into a lower orbit, for example, orbit 4 into orbit 3, then this process right here would release energy. And now this energy right here being released in the form of a photon or a wave. So in this case right here, this process is then called relaxation. So relaxation is whenever we have an electron that jumps from a higher orbit into a lower orbit, and in that process it releases an amount of energy in form of a photon, and this photon right here will then have certain amount of energy to it. And similarly, electron can also jump from a low orbit into a high orbit, for example from an orbit 3 into orbit 4. In order for the electron to jump from here to here, it needs to absorb energy. So we actually have to put in energy in form of a wave in. So in order to make an electron jump from a low orbit into a higher energy orbit. So in this case right here, energy is being absorbed. And this process is then called excitation. So excitation refers to the jumping from a lower orbit into a high orbit. In this case, energy is required or being absorbed in order to make this process work. So that's what relaxation and excitation are in the movement of electron. Now, so here is another example. Let's say here we have the nuclear, and these are the different orbit 1, orbit 2, 3, 4, and so on. So when electron can jump from orbit 2 into orbit 3. And in this case right here, when it go from lower orbit into higher orbit, it will then require energy. And the reason why as follows: the orbit 1, this is the one that is closest to the nucleus. And because it closest to the nucleus, it then have lowest energy. Versus the higher the orbit, then the further it is from the nucleus. So this is farther from the nucleus. And this is then said to be higher in energy. So as an electron jump from orbit 2 into orbit 3, it goes from lower energy into higher energy. So therefore it has to absorb energy in order to make it work, right? Because we can't magically go from lower energy state into a higher energy state without the extra energy being added. So in this case right here, energy is required in order to make this work. Now, how much energy is required? Then the answer is as follows. The energy required is then equal to the energy difference of this third orbit right here minus the energy of this second orbit. So the energy required within energy of the third orbit minus the energy of the second orbit. And that tells us how much energy that is needed for an electron in the second orbit to go into the third orbit. And again, this is excitation. This process is called excitation. And now on the reverse direction, electron can jump from the third orbit down into the second orbit. So it goes from higher energy into lower energy. So when it goes from higher energy to lower energy, it has to release energy, right? So if energy is being released in the form of a photon. So the photon is being emitted because a photon is basically a package of energy. And in this case right here, the energy of this photon that is being emitted right here is then equal to the energy of the third orbit minus the energy of the second orbit as well. So it makes sense. It to go from here to here would require a certain amount, and that amount is the same amount that is being released when we go from the third orbit down back into the second orbit. So that's the third statement from the Bohr model right here. The electron can jump between orbits, and in the movement, then now a discrete amount quantity of energy that we call quanta. In this case right here, a quanta is similar to the word photon. So quanta is a quantity of energy, and in this case right here, a photon has certain amount of energy in it as well. So they both kind of refer to the same thing. In this case, energy is being released. And so during the electron transition, a specific or quanta amount of energy is being involved, either required or absorbed, and the photon need to have this right amount of energy right here in order for the transition to happen, no more or no less. For an example, if we were to give it not enough energy, let's say half of the amount, they will never be able to make an electron jump from the second orbit into the third orbit, but it has to have that right amount. And similarly, if we were to give this too much energy, then it will not do that either, because it has to absorb a very specific amount of energy. That is the difference between the second orbit to the third orbit in order for that transition to take place. Now, so how did Bohr come up with this model right here, and why did scientists actually accept his model? Then consider the following observation that he did. So Bohr performed something that we call the emission spectral experiment, and this is what this experiment is. So he took a hydrogen lamp and he would then heat it up, and just like all of the lamp, when we turn on the electricity, it will be producing the lights. And now the light then produced by this hydrogen lamp is then allowed to pass through a slit, which basically allow only one direction of the light to go through but block out the other direction. And this light right here, after it passed through the slit, it then passed through a prism. And a prism is basically a component that separates lights into the individual component. So the color that we see here, this light right here that initially being produced that we can observe with our eyes, then this is basically right here the overall color of all of the waves that are being produced by this light right here. But once we pass this light right here through a prism, we found that it will be split into individual components, and each of this individual component right here is a wave, and each of this wave right here would have certain amount of energy to it that would then correspond to certain color that we observe here. And we know already that this color right here, each of this band or line of colors right here correspond to a wave of a particular wavelength to it, and that's what we observe right here. So that, and this is called the heat emission spectrum. Now when we heat up different elements and we to produce light, and we then pass it through a prism, and then we observe the emission spectrum, we would see the following. So here is the emission spectrum of hydrogen, and here is the emission spectrum of mercury, and here is the emission spectrum of neon. So every element have its own unique emission spectrum, to the point where we refer to this as the fingerprints of the element. So every element is uniquely different than other, and this can actually be used to detect what types of element it is by looking at its emission spectrum. So every element has its own distinctive line spectrum. So we call this the emission spectrum, or also the line spectrum, and the reason because we see in different lines in here. And again, each of the discrete lines that we observe on the emission spectrum correspond to a photon or a wave of a particular energy and wavelength to it. So how did this emission spectrum right here help support the Bohr model of the atom? So let's go over this. Now, so it turned out the following. Each of the line observed on the emission spectrum is due to the electron transition from higher energy orbit into a lower energy orbit, just like what we have seen in one of the statements that Bohr proposed, and that is known as the quantum jump. So a jump from one orbit to another orbit. So this supports the idea of the quantized energy level or orbit, and how electron can be transitioned from one orbit to another orbit. For an example, here is the emission spectrum right here, and we observe these different lines of color right here. So where this different line of color coming from is basically due to electron transitioning from one orbit to another orbit. When electron jump from the fifth orbit down into the second orbit, it is producing an amount of energy, right? So it producing a wave, and the amount of energy that being produced here in this case right here would be high. So the wave that it producing have higher energy, and here in this case it would then correspond to a wave that corresponds to a violet color. Whereas the line here in blue-green basically is also due to another electron transition, and in this case right here, the electron is transitioning from the fourth orbit down into the second orbit, and in this transition right here, it released a smaller energy compared to when electron jump from the fifth down to second. So again, when electron jump from fourth down to second, it also released an amount of energy, but here in this case a smaller amount, and therefore it now producing a photon or a wave that have lower wavelength to it. So here in this case, higher wavelength to it, or lower frequency to it, and therefore in this case it corresponds to the blue-green color. And similarly, when electron jump from a third orbit down into the second orbit, then it will be releasing a package of energy as well, or a photon. And this wave right here, so the wave of this photon right here, it have lower energy, and that will correspond to the red color. So that's where the emission spectra come from. And only when the structure of the atom is the way the Bohr proposed, an electron are allowed to jump from one orbit into another orbit, that we will be able to make sense of this emission spectra that we observe right here. So this is the reason why that this data right here supported the Bohr model. And now we also see the following: electron can only jump from one quantized orbit to another quantized orbit, but never in between. So that is a very important thing right there that we have to remember. So in this case right here, the quantized orbit, electron can only jump from orbit to orbit, but never in between. Because if electrons are allowed to jump simply from anywhere to anywhere, then that anywhere would be expected to observe a continuous spectrum. So the continuous spectrum is basically a spectrum where we see all of the color. And the reason why we see all this color right here is that there's all kind of waves in here that have different wavelength, and therefore they correspond to every color that we see on this spectrum. And so we would expect to see a continuous spectrum if electron can jump from any orbit into another orbit. And the reason why as follows: let's say if electron can randomly jump from here to here, it will be producing one wave, right? When it jump from here to here, a little bit more, it can produce another wave. When it jump from here to here, it can produce another wave. So basically, all kind of waves will then be possible. And this is why that all kind of color be possible. And we would have expected to see a continuous spectrum. But in this case, with the emission spectra of an element, we do not see a continuous spectrum, but we see in this discrete line spectrum right here, only certain color are observed, but not all color. So that tells us that electron can only jump from certain place into certain place. So that's very crucial, that supported the ideas of the Bohr model as well. So in conclusion, we see the following: the Bohr model provided a reasonable explanation for the discrete atomic line spectra in terms of electron energies. And it introduced a very important idea, which is the idea of the quantized electron energy. So that's what those quantized orbits would be in the atom. And this idea of quantized electrons energy right here, this provided the foundation for us to further understand the quantum mechanical model.